Yes, I thank the organizer for giving me this opportunity. Today I will in part review a model that was proposed 10 years ago. And on the other hand, I will show some recent developments because we have worked on it recently. It's a work that has involved a number of people in the last 10 years, essentially, both numerically and analytical work. So, I have the advantage that more than something has been said about QPO, so I will be brief about a review of observational evidences. Then I will show the dynamics of this thick disk, geometrically thick disk around compact objects, and then I will describe this model, also in view of recent discoveries. And finally, some comments and conclusions. So the observational evidence is not so large, I would say. From a physical point of view, we only have 20, something like 20 neutron star binaries showing killers, QPOs, and much less 8 black hole binaries. And as we have heard, they are just weak and elusive features in the power density spectrum associated to non-thermal states. Most of the time is the particle phase. Although the phenomenology of this observation is similar in neutron star binaries and black hole binaries, there are also some differences, and it's upon these differences that a lot of attention has been focused, I would say. For example, killers QPOs in black hole binaries are much more stable. They shift less than in neutron star binaries. And then, for example, black hole binaries also display jets, suggesting the role of an accretion disk. There is also this indication that the difference between the two, because they quite often appear in couples, the difference between the two killers QPOs is related to the spin frequency, but this is only valid for neutron star binaries. And there are also some other interesting issues concerning the ratios of this frequency. I will come to that later. So the general idea is that two different mechanisms are responsible for this behavior, although there are several ideas about this. Sorry. So this is an example of a neutron star binary. It's a very beautiful source, XTE J1701. And in this case, the two killers QPO frequency are really one double of the other. Okay. Another example is a black hole binary. This is another famous source, J1550. And the observational evidence for black hole binaries has this interesting and well-known peculiarity, because in the four sources where the pairs have been observed, they appear in this frequency ratio 1.5 most of the time. And then for the famous GR 1915, actually you can identify more than a couple. And in some cases it is 0.1, 0.0, or in other cases 1.5. So even if so limited, because these are only four sources after all, we are trying to explain this phenomenology and to build the physics of this. In the case of neutron star binaries, we don't have the same strong evidence. There are, yes, indications, but if you plot, as Belloni did, the upper and the lower QPO frequencies in a diagram, you will find out that, first of all, neutron star binaries have these frequencies scattered along lines. It's not just a point, because they change much more. And moreover, they don't follow a simple 2-3 relation. So you have to try to explain why they cluster along those lines. And several models have been proposed. It's embarrassing just to list them without a proper comment about them, but I really don't have the time. So over the years, bit frequency model was proposed, the Rayleigh-Taylor gravity wave model, relativistic precession model, the resonance orbital model, the trapping non-axis metric model, in connection, I think, to gravitational stability model, the acoustic model I'm talking about here, the MHD Fan wave model, magnetospheric boundary layer model, tidal disruption model, and multi-resonance orbital model. I mean, I've read them just because they are involving a lot of physics, and it's interesting to to see a strong debate that can be produced over, I repeat, a small sample of data after all. Okay. So the idea we proposed 10 years ago is that kilohertz QPOs can be interpreted in terms of internal pressure modes in a thick, geometrically thick disk, not a thin one. And this idea was developed both numerically and analytically, and we show both the approaches until recently, until last year. Geometrically thick disks are very old-fashioned objects in general relativity. In a sense, they come from the solution of the Euler equations in a fixed background spacetime. They are non-Keplerian objects. The rotation law is non-Keplerian. And if you plot the Keplerian one here in the meridional plane, and you intersect with a constant specific angular momentum distribution or the power law, you will find out that these objects have two spatial points, a cusp and a center. This point here and this other one. And you can feel the potential well in different ways, producing an object which has a minimum an inner radius and an outer radius. This is not just a theoretical analysis. Actually, okay, you have different possibilities because you can have an object which is completely enclosed in the last equipotential surface, or you can have an object which is fully filling the closed equipotential surface, or is even overflowing it. So the analysis you can do about this is quite clear, but it's not only an analytical prediction, it's also the result of a fully relativistic numerical simulation. Let me see if I can activate from here. No, so probably have to. In this case, the initial conditions are given by two neutron stars that are coalescing and then merging. This is a fully relativistic simulations. The two neutron stars do not have the same mass. There is a 0.8 mass ratio. They produce a black hole, and after that, as you can see, there is a torus coming out. The size of a torus is around 15 gravitational radii for a black hole of 3 solar masses, and its mass is increasing with the asymmetry of the binary system. But the final story here is that these objects are not just a speculation and are the result of the most accurate simulation that can be done at the moment. One of the limits of this approach is that once the torus is produced, you cannot really follow the dynamics because this simulation is so time-consuming that we cannot follow for long. So 10 years ago, we did this. We followed the dynamics of in two-dimension numerical simulation. We perturbed the equilibrium solution, and we saw that the system is reacting to the perturbation by producing a periodic accretion through the cusp, and is oscillating. And this was the oscillation that attracted our interest, and based on this, we proposed the interpretation that kilohertz QPO could be these P modes. In this case, you see there is really accretion of matter through the cusp, and incidentally, there is also emission of gravitational waves, but this is not pertinent to our focus today. You can determine the periodicity, I mean, the synthetic spectrum out of the numerics, and as you can see, there is a fundamental mode of oscillation F, and then there is an overtone O1 and a series of overtones. And also modes at exactly the double and 3 times the fundamental frequency. So producing this, there are a number of lessons from this spectrum, because producing this double frequency is not at all difficult. It's a known result of dynamical systems governed by nonlinear equations, that if you have genuine modes of oscillation, you also have the nonlinear combinations of them. Sorry, the linear combination. So F, you have also F plus F. If you have F and O1, you also have F plus O1, as you can see, actually. So whatever your physical system, this is a lesson to learn. whatever your physical system, physical mechanism for producing F, you will always have 2F. It's not difficult to have it. In addition to numerical simulations, you can perform a linear perturbative analysis. Of course, it's fundamental to understand the physics behind. And so we did that in those days with a number of approximations, assuming vertically integrated quantities. The equations in the box are the linearly perturbed Euler equations in a Kerr spacetime. I'm not going through the details, but you can see there is a perturbation here in the velocity, radial velocity, in the phi velocity, and in the pressure. And assuming this sigma exponential dependence in time, as usual, you can extract a dispersion relation with two distinct contributions, an acoustic and an inertial one. Now, the inertial one is actually the epicyclic frequency, which in the presence of pressure gradients has these corrections, because the P over dr, there are other terms here, so it's different from the simple epicyclic frequency in a geodesic approach. And the surprise is that if you assume a power law distribution of the angular momentum, the epicyclic frequency is monotonic. Is no longer does not have longer the monotone, the maximum as we know in general relativity. So you lose the wave trapping region. This is an example. This is the epicyclic frequency for a power law distribution is not does not show the maximum, no, that we are used to have, and so there is no wave trapping region. There is, of course, an evanescent wave region and a propagation wave region. But then you can, of course, compute your eigenvalues and eigenfunctions. I mean, really the form of the perturbation. And what you get is that the frequency ratios, these are computed as eigenvalues of the eigenvalue problem, come out in this ratio here, which contains the 1.5 observed, and in that other one, which is approaching 2. So from this, you can extract some astrophysical information. The idea that I'm expressing is this, that the p-modes can be responsible for the kilohertz QPOs, and because there is this property that as you decrease the size of the thick disk, the fundamental frequency tends to the epicyclic frequency. I will show you a plot later on. Then you have the consequence that your lower kilohertz QPO frequency must always be smaller than the highest possible epicyclic frequency. And what does it mean? That if you have an observation like this, the day a lower kilohertz QPO would be higher than the maximum allowed epicyclic frequency, the model would be confuted. On the other hand, if you have your observation here, in this case, you assume this source XT J1550. If you have an observation here, you can extract a lower limit on the spin of the black hole, because, as I said, it has to be the observational frequency has to be always smaller than the maximum epicyclic frequency. Then you extract such a constraint on the spin. And this is, I think, one of the good points. Now, does this work for neutron star? Because what I said so far was actually focused for black hole binaries. And last year, with Pedro Montero, we extended the analysis, the linear perturbative analysis to neutron star binaries with a number of approximations, but we used the Alpha-Length Thorne spacetime. We sampled a much wider parameter space. You can build a huge class of models here with a different angular momentum distribution law. And what you see here, there are 3 classes of models: constant angular momentum, power law, but the power law B class is even wider because there is a range for the exponent Q. And so each of them contains a lot of more model. We confirmed some of the findings for the black hole binaries. For example, as I was saying before, as you decrease the size of the disk here, the frequency f, the fundamental one, converges to the epicycle frequency because actually your disk is collapsing into a ring, and so it oscillates like a ring. And the frequency ratio, if L is just a constant, behave like this. So you see, it's not just 1.5. It can span a range here. And if the power law, if the angular momentum is a power law, it's even wider, the range of the ratio O1/f. And it approaches 1.44 for a very large radius. All these curves here are around 1.44. So the model is not just saying you have to have, you need to have, you must have 1.5. You have a wider range of values possible. But there is a defect which we highlighted. At the moment, we cannot explain the phenomenology reported, namely that our computed models only partially intersect the observations here for neutron star binaries. And so there is something we are missing. This is the O1 mode. So in the interpretation that the half per kilohertz QPO is O1 and the lower one is F, we produce these results. If we change O1 to O2, we have another intersection. Some of the models are, of the observations are captured, but others are not. And so there is, in our opinion, some physical ingredient that we are missing for the neutron star binaries. Coming to the end, there are some advantages of this approach, which is a very successful idea for black hole binaries, and the idea is effectively also simple, because P modes were studied in the past for a long time, and frequency ratio 2, 3, 4 are naturally explained. As I said, the frequency ratio 1, 2 is trivially explained. We don't need to justify the preference of specific orbits, radial orbits, where the emission is confined. This is a global mode, so in particular, we don't have a wave tracking region. For the future, we are, well, my plan is to add more physics to this picture, which remains simplified. And there may be hidden variables who are not so hidden. One of them is the magnetic field, but the magnetic field is possibly not changing drastically the situation. For example, the toroidal magnetic field for sure. The poloidal one, probably not. One of the problems is that we don't have an equilibrium solution with the poloidal magnetic field, so the linear perturbative analysis is in trouble. But what is really missing here is radiation. So one of my present field of research is radiation hydrodynamics. And on Thursday, I will present another talk with radiation hydrodynamics in general relativity, with the future idea of making a link with this phenomenology. Now I will abuse of your patience for 10 seconds to promote a book that we have written recently with Luciano Rezzolla. You can find a copy for your inspection in the coffee room. Thank you for your attention.
Thank you very much.